So Craig, you do mill tailings before we get started. Did I ever show you that picture of Frank that I have where he can't, when we're in Henyang near the uranium mill tailing site? Are you familiar with that one? They have a valley and they put up like 11 or 12 dams. And they took all the mill tailings from all over China from the domestic nuclear production and put them in one place. And they were trying to figure out how to cover it. So I think I told you, so we drive up. It's on top of this valley, and there are all these radon detectors. And I'm like, do those ever go off? They're like, yeah, they go off all the time. So we shut them off because they're a nuisance. You're muted, Craig. Sorry.
Crescent Junction is like that to some degree. That's where a lot of things from Moab and like are being consolidated, and Grand Junction Disposal Facility is another one like that. But they don't have radon detectors going off constantly.
Well, they didn't either at this site because they turned them off.
So, so Judy, I think we should kick off, right? So, yeah, okay. So good afternoon, everyone. This is Nick, and nice to see you on this cozy Friday. And so first, before I introduce Josh for the seminar, and I want to make an announcement. The Waste Management 2023 conference, the abstract is due today. So I want to let you know. So if you want to submit the abstract, do submit it today. And it's a great conference. I made the last 3 conferences, and especially the last one, I feel very good because we have the CRESP Early Korea gathering, and know a lot of people, especially meet Kevin in person, and a lot of the Early Korea programs friends, Josh, Rupanjali, and Steve, met you guys. Very happy. And I submitted one, and I don't know who else submitted. I think Masa is also especially want to like organize also another gathering for next year. So if you submitted one, please drop yes in the chat so we know who will join.
And Nick, just a couple. So 1989 was my first waste management conference. When I was young like you guys, even though my kids don't believe I was ever young. And so it's a great conference. It's changed a lot over the years. And what they're saying is the abstracts are due today. But if you send them in late, they'll go through a second round of review before they're accepted.
Okay, good to know. Good to know. Yeah. Okay.
Nick, could I say one thing before you go?
Yes.
I just want to announce something special about one of the members here today. UTAN received a EREF scholarship, PhD scholarship. These are from the Environmental Research and Education Foundation. They're hyper competitive, and you got one of those scholarships. I think that was announced last week or maybe 2 weeks ago. Congratulations.
Yeah, congratulations.
Yeah, thank you all.
Congratulations.
Congratulations.
Yeah, by the way,
Can you send me the information for that?
okay, sure, okay.
Thank you.
Okay.
Sounds good. Yeah. Okay, so let's back to the major topic. So I want to introduce Josh Hargraves, who is also, everybody know him. Is our chair of the CRESP Early Korea Program Committee. And so some details about Josh. Josh is a PhD candidate from the Oregon State University School of Nuclear Science and Engineering. And he has become the primary graduate researcher on a fatal remediation project in the area Colorado Plateau, addressing contaminants of radium, uranium, and other trace metal elements within the area of legacy uranium mining site. In addition, he has experience with statistic analysis, having spent 3 years as an analyst with the public, government, and the medical records industry. Before he earned a Bachelor of Science in Physics through Illinois State University in 2014, specializing in biophysical neurology modeling and nanoscale engineering. So he is also member of the Health Physics Society as a Berkeley Fellow and a member of Sigma Pi Sigma, the Physics Honors Society, directed through the American Institute of Physics. So, Josh, I just hand over the microphone to you. Yeah, please start your presentation. Thank you very much.
Absolutely. Thank you for the wonderful introduction. And yeah, once again, I'm just Josh Hargraves. I'm the head of the Committee for the Early Career Planning program. And today I'd like to talk very briefly, perhaps, about the utility of endemic species in site management. So just a really brief overview for those who are unfamiliar with uranium mining in the US. A lot of our concentration for mining actually came to look for radium-bearing ore, because radium-bearing ore from 1898 on was really used for all the medical, ceramics, and photography innovations that were coming out in that period. It wasn't until we actually came about this wild concept called fission, some of you may have heard of, that we actually started looking at the uranium sites for the uranium itself. And so this created a kind of boom in a lot of areas. A lot of these kind of arid and somewhat isolated areas became really hot spots for uranium mining. And in particular, we're looking at the Colorado Plateau. The Colorado Plateau kind of encompasses a few different states. You have both Colorado, Utah, New Mexico, and Arizona. The sites that we're kind of looking at in general in this kind of context will be more on the New Mexico side. And over on the right, you can kind of see just a concentration of where we have these individual mining claims. And for the most part, we did really great at mining uranium. We've developed a lot of really novel techniques and can get out of the ground really well. On the flip side of things, we made a really, really bad effort to make sure that all of the contaminants from all of that processing and mining didn't go everywhere else. So the site that I'm looking on, again, is Ambrosia Lake, which is just a little bit outside Albuquerque. It's closest to Grants, New Mexico. And it's a very arid region. You can see that the plant cover is very low. The soil itself is very easily wind tracked, and a 1 acre contaminated area can easily become 1,000 contaminated acres if you just let the wind take it. The site I'm looking at has had its own share of history. You've had it owned by private contractors, then it was acquired by Rio Alga Mining, and now it's acquired by Broken Hill Proprietary, a giant mining conglomerate out of, I believe, Australia. However, all of this is eventually becoming legacy site and needs to be handed over. In particular, I went to 3 sites within this area, dubbed by the owners as sites 17, 22, and 35. And so I'd be remiss to not talk about the actual history of the town proper of Grants. So Grants was actually known as the uranium mining capital of the world. And as soon as the main uranium mining boom died down, it immediately became a post-boom town and essentially is becoming more of a ghost town. There's a bit of a problem there in that many popular publications, especially news outlets and other media that surrounds the town, has a very unflattering image of the nuclear industry and what we've done in the region. Now we also have native communities and mining claim holders that still hold those lands, or ranchers that now live beside those lands, having extreme risks and concerns about environmental and personal risks that they may encounter. So we're looking to solve this with phytoremediation. Phytoremediation, for those that are unfamiliar with the term, is to use plants to try to remediate or at least stabilize contaminants in the soil. So this is really just going to be looking at the topsoil of these areas, because you can only go as far as the plant's roots can extend in phytoremediation concerns. In particular, we're looking at endemic species. This is for a few different reasons. One is that the endemic species, we know that they already exist there. So you're not going to try to introduce a new species that will require either more water or kind of soil amendment to alter the actual kind of structure of the soil itself, or try to bring in more resources that otherwise would just make a bigger headache for remediating the site. The other side is that we want to use endemic species to maintain the ecology of the region, because otherwise you're changing the area entirely. Of course, the flip side of this is to always do the traditional way of just excavating the entire land and putting it into fills. However, when we're talking about thousands of acres, that equally racks up into the millions and perhaps even billions of dollars. And these plants can take in these contaminants through a variety of means. So the primary transport mechanism will be through the roots. The roots will uptake a lot of these contaminants through either actual soil absorption into the root structure, or they'll be hangers on to other molecules that the roots are uptaking. In addition, there will be a somewhat side dose, just because it's such an arid region and you'll have a bit of aeration, bring some of that dust onto the plants. And when I talk about concentration contaminants, what I'm particularly looking at uranium-238 and radium-226. Now, both of these kind of migrate at a similar pH, and they get held right into that soil organic matter. The uranium itself does not actually partake up by itself as kind of a chemical analog. It'll hang on to any oxygen species that are within the area. So any water or any kind of soil oxygen content, it'll try to grab onto that, and that is how it gets transported into the plant species. Radium, on the other hand, actually acts as a chemical or biological analog. Depending on how you may have learned these techniques, chemical and biological analogs can act as surrogates for certain other chemicals. So radium can act like calcium, which is very crucial to a plant's growth as it creates its meristematic tissue, and especially once it gets to the seed-bearing stage. And so to analyze contaminants, we have the privilege of having the TRIGA research reactor at Oregon State University. So activation to look at uranium is a really easy way for us to go about looking at the uranium content, just by activating it to plutonium-239. Radium, on the other hand, we looked at gamma spec via high purity germanium detectors. Now, there's a little bit of a caveat with the gamma spectroscopy, because if you have a sample that contains both uranium and radium, your spectral lines are going to overlap at the 186 keV line. So what do? Well, radium-226 also has the progeny of radon-222, and that has further progeny of lead-214 and bismuth-214. So if you seal these samples and then wait a period that you get equilibrium state, you can then measure both the lead and the bismuth as a fraction, as a surrogate, to identify how much radium was in the samples. Activity is really just simply calculated for those HPG results by just looking at the bulk counts, subtracted out for any of the conflicting kind of background, as well as just detecting the efficiency of the detector and all of the usual things you do with a traditional detector arrangement. And of course, you'd be remiss to not look at some of the statistics to make sure that what you're looking at between these sites actually has variation. Because if you're going to compare what these sites are doing, you want to make sure that each of these sites is different in some way. And this can really just be done by a simple ANOVA-Bonferroni analysis, just look at the variances between the sites. And for the most case, they do have some variation. And kind of lucked out in that the 3 sites that we chose had a pretty good linear correlation. So this allows us to then, once we've finished this kind of process, we can look at how statistically well plants will do on either side of these concentration gradients. So this is all well and good in theory, but then you actually have to go out to the site and grab things. So we actually did go out there and grabbed probably close to 20 gigantic painter-sized buckets of soil, as well as, and this was just the first grab of 147 different plant species, 147 plants, that is, of a variety of species. I want to note that some of these are invasive, and that's where the topic of endemic comes in, because some of these have either been brought in as invasive species unintentionally, or some of them have actual indigenous people's use and some of them have been brought to the site as part of that kind of community. So it's important to look at all of these as a whole as endemic species, just because they're already there and we know that they can live there. And among those 4, we chose 4 candidate species that were prolific between the sites. We chose alkali sacaton, which is just a common grass of the Southwest, summer cypress, also known as burning bush or Kochia scoparia, 4-winged saltbush, which is a pretty molybdenum-heavy kind of graze bush, and then the common sunflower as just a common flower surrogate. And we took all of these and we grew them in a greenhouse at OSU in lysimeters. Lysimeters, in the simplest case, are really just a pot with a ability to keep water pressure at a stable level. And we lucked out in a sense that these were very clay-heavy soils, so there's not a lot of actual water table balancing with a pressurized system that you need to do, because the water is already going to be retained in the soil mixture itself. So you can really just create a pea gravel or very straight to limit the water reduction. And some of our plants did grow, so success. And we did this across all 3 sites for all of our different candidate species. And when we take these plants out, we measured them in the same way that we went about the soils. So we took the plants before we actually started throwing them on the detectors, and we cleaned them with deionized water, and then I chem wiped off all of the particulate matter that may have adhered to separate out any contaminants that it would have been in the soils from what is actually in the plant. And I separated these into 2 different endpoints, the root tissues and the shoot tissues. Shoot tissues being at least 1 centimeter above any meristematic roots. And of course, like you just heard about waste management, I actually talked about this at waste management this past year. So there's a lot of information on the slide that I'll go into individually, but the biggest thing that I want to look at is our end goal, is to look at the bioconcentration factor. And that is just the ratio of how much of these metals have you found in the tissue compared to the growth media. And that tells us how well we can use these for either phytoremediation or phytostabilization. So for the lower end, section 22 had the lowest concentration initially. For the radium, we see quite a few plants did very well, and quite a few actually partitioned into the roots more than the shoots, which identifies that these are going to be a much better phytostabilizer. Now, if it's more in the roots and stabilizing is your goal, that's the goal. If it's more in the shoots, then you can actually extract these plants and move them off-site either as biochar or any other process that may be easier for site management in the future. And here is just kind of graphically represented. I did many replicates of these plants. Each of these color dots is representative of a different plant. So if you see shoot replicate 1 and root replicate 1, that just means the first replicate of that sample, and then so on. And we looked at the higher end. At the higher end, radium did not transport nearly as effectively. However, we did have a little bit of promise in alkali sacaton and summer cypress. And this is just, again, the graphical view of that. And then looking at the uranium, at the lower end, sunflower by and away was the overwhelming winner here. At the higher end, again, these did not go over too well. So there's clearly kind of a concentration cutoff in which plants just have more of a toxic reaction to these metals than an actual uptake mechanism. So just as a quick takeaway from this, we're looking at phytoremediation, and we're looking at the transfer ratio relative to the tissue, and that will determine whether we can try to remediate the area or if we can just stabilize the area. We're looking to establish more of the radioecology of the area because very little data actually exists about any of these plants. And at that point, you kind of have to look at ecological level studies rather than individual non-human biota kind of comparisons. And I think the biggest part on the flip side of this is that when we look at phytoremediation, this is going to be something that we discuss as generations and not just a seasonal, here we can plant this and suddenly the area is clean. However, it's far more effective, I believe, monetarily anyway, than simply disposing of all the soil. at the same time, we have to make sure that we're keeping our conversations relational. Like I mentioned prior, the community is very hotly debated over this topic. And so when we come to address these concerns, especially if using endemic species in the region, we need to make sure that the science is not obfuscated and that we can reach out to communities not as victims of the area, but try to work with them to remediate. And that was perhaps a very brief synopsis of some of the work we're doing here, but I thank you for the privilege to talk on it, and I welcome any questions. See a question from Kevin.
Yeah, I was going to say, typically we want the students to go first. So if anybody has a question who's a student, please go first.
And thank you, Josh. So, I have
Right.
I have just a like very preliminary questions, like for the vegetations you choose, what's the principles you for that? I mean, there's something like site available, or you choose from literature. What's your principle in that?
Yeah, so the biggest drawing factor was looking at proliferation between sites. And that was just to ensure that when we look at these plants, we can identify that they're along this gradient, how well they do along this gradient. And that will allow us to see, okay, if we have something that's lower or something that's even higher, how well will they do in those regions, or how well will they do between those regions?
Okay. Well, what's the time scale for the take up?
Yeah, so plants can take up really just as long as they reach until they reach maturity, and then they start to kind of decaying. But as long as the plant is alive, it's taking in these contaminants. I want to really stress that when we're talking about this again, that this is going to be like if you do something like this, it's generations of human generations of remediation and stabilization. This isn't like a band-aid that here we just sowed a bunch of seeds in the field and now it's going to be clean. Is going to be many, many, many generations of replanting and maintaining the region.
Okay. Oh,
yeah.
Thank you very much.
Yeah.
Okay, if there are no students, so first my comment was, Craig, I don't know how much more orange I can take, but you were at UVA, so you're probably used to it. And at least it's not big orange like UT, so I guess I'll give it a pass. So when show some of your BCFs, I noticed lots of significant digits. Back when I was doing transfer factors and things like that, I would never have believed 4 significant digits on anything related to something like that. So typically when I look at something like this, how do I put it in the context of uncertainty? Because typically what we really run into with these things is they're very highly variable and uncertain. If you believe those are different components of uncertainty, and most people say it that way. So I was just kind of curious about how I look at this and make sense of it in terms of uncertainties.
So in terms of uncertainties, just, I guess, how I came about these degrees of uncertainty?
Well, no, so typically in a transfer factor, you know, often, you know, I was doing this a long time ago. So the transfer factors back when I was using unscore, you know, 1993 and later, you know, if you're an order of magnitude, you might believe it to an order of magnitude, you know, things have gotten better. So I'm just trying to put this in the context of, you know, how many significant digits really, and what's the uncertainty associated with something like this?
Yeah, it really is going to come down to the uncertainty of the detectors that you initially got these concentration values from. So it is how well you've calibrated those detectors initially.
Well, there's also the issue of I'm selecting plants in certain areas. There's going to be variability from plant to plant.
Indeed.
So how you know, Craig, I asked this for Craig the other day of how he designed his site when he was doing a mill-tailing site. So how do you make sure you get a representative sample so that sort of uncertainty and variability is subsumed within you actually doing the collection in the first place?
Oh, sure. Yeah. So, I mean, it comes down to having that number of replicates initially too. So there's a kind of a balance between replicate statistical strength. And that's kind of what we try to look at least. So for at least this many sites, trying to get at least 5 to 10 replicates gives us a statistical strength to at least look at these plants.
So you did that, you assumed an uncertainty, and then you used that to figure out the power that you needed in your sampling.
Indeed, yeah,
Got it.
exactly.
Thank you.
Yeah, yeah.
Hey, Josh.
Yeah.
Well, I got a question. So, you have mentioned about you try to clean those contaminant site, but what's the meaning of clean? Because and the question is, how low the country you try to clean the site, but how much you can reach? Because you cannot
Right.
clean everything. What's the lowest concentration that you can reach at the site by this technique, and how long it may take? So Nick had asked about the timeline, but how low that you can reach by this technique. And also, I think it may depend on the initial concentration before you apply this technique in the field, right? This may
Right.
also affect the rate of the clean. Yeah.
Yeah, absolutely. So it comes down as far as how much you can clean, goes as far as the roots can go, essentially, and that's going to vary plant to plant. You can kind of create an estimation of how well these do. Some of the grasses can reach pretty deeply. The alkali secton can get up to 1 meter with root structure. However, if you look at something like the sunflowers or the kind of the summer cypress, they have a much shallower root structure. So you're probably going to get at most maybe like 1/4 of a meter down. So it is going to be something that is very variable, and it's going to be kind of a throw science at the wall and see what sticks, in a sense, when you try to go between these sites, because every site is different, and you can even have that intervariation between sites.
Yeah. Okay, thank you.
Yeah.
I guess I'm up. Yeah. This is kind of a segue from your application, but we have lots of closed sites out in that region as well. One in Grants, New Mexico. And in that Colorado Plateau, actually 3 of our field sites are in that area, the Monticello Disposal Facility, the Grand Junction Disposal Facility, and the White Mesa Mill, kind of almost right on the right-hand side of that.
Okay.
And both in Colorado and in Utah. Historically at closed sites, DOE's approach has been to spray the vegetation to prevent any vegetative growth on the cover from the perspective of minimizing the potential for radionuclide uptake and potentially uncontrolled release. It's never been clear though whether that was necessary given the thickness of the cover and whether those root structures would actually reach any contaminated material, because the cover is built out of clean material.
Right.
I guess a question I had is, there are a number of old closed sites out there, and while the intent was to keep them denuded of vegetation, that hasn't always been the case. And have you thought about maybe using the same approach, the same set of tools, and maybe going out and studying those?
I'd love to.
Because that would answer some of those questions. You know, how important is this for closed sites that have been closed with historic approaches? LM did some work on it. DOE LM did a study with the Navajo Nation where they indicated it was not particularly significant, but fairly limited as well. So that might be something you could segue out on this in the future.
Absolutely, yeah.
So more of just a suggestion than a question.
Sure.
Yeah. Hi, Josh. This is Paul. I have a question regarding the soil concentration and as well the concentration in the shoot and the root.
Yeah.
Do you see any correlation about if the soil concentration is high, the concentration in the vegetable is higher, or the vegetable only absorb certain amount of this kind of radionuclide?
Yeah, so that's what we're trying to identify with the concentration gradient, is to just see how much is partitioning each subsection of the plant. And yeah, that was kind of what I kind of tried to hint at with here, and then at the higher end at section 35, is that these lower ends, it seems to be partitioning into the tissues a lot more readily and actually being bioaccumulated in some sense. Whereas at the higher concentrations, it's almost having a toxic inhibitory growth effect and is not being taken into the plant nearly as much.
I see. Yeah. The reason I ask is recently I see a study. People try to measure the concentration of different type of contaminant in vegetation, and then mapping the contamination in the soil. Then rather than measure the soil contamination, they measure the plant and then reflect about what's the concentration in the soil historically and currently the deposition there. That's why I'm interested to see whether you see any correlation between the soil concentration and the vegetable concentration.
Yeah, that's essentially what I have seen here, at least a beginning of a preliminary assessment that at these lower concentrations, it does migrate, higher concentrations, no. So I guess you could have an idea that if you are just doing that kind of forensics almost of taking the plants and trying to figure out what was in the soil, you're going to have quite a bit of a leading area depending how hot that was. Because if it was too hot, then it's not going to accumulate in the plants. And you could have a very different idea of how much was actually in the soil initially.
I see. Yeah, thanks.
Yeah, of course.
Josh, I just had another thought or a comment I wanted to add.
Sure.
When you were talking about kind of in the heyday of mining, we were mining and milling uranium ore in that region, and we did create a big mess. But at the same time, people didn't really appreciate that it was a mess, that it was a contaminant problem. If you go up into Colorado, into Grand Junction, a lot of the infrastructure in Grand Junction was built on mill tailings. They used it as fill.
Sand, yeah.
And so, I don't know, it was 25 years ago, maybe more, maybe 40.
They tore a lot of that up, didn't they, correct?
Oh yeah, it's all been cleaned up, and a lot of that's in the Grand Junction disposal facility. But it was, people's homes, the foundation around their home, they would backfill it with tailings because it was just great to backfill. This nice fine sand that leveled easily. It was just fantastic. Yep. Nobody really understood that it was radioactive. And actually, Jody Waugh, who's with DOE-LM, who I worked with for years, his home as a child there in Grand Junction was one of those homes. So if you ever want to learn about that story, just go reach out to Jody. He's at DOE-LM.
Excellent.
Yeah.
Panjali?
Yeah. Hi, Josh.
That's good.
Thank you for the amazing talk and for introducing, at least to me, to the concept of phytoremediation. I just had like a couple of basic questions. So I was wondering if there has been, or were you able to establish a correlation between maybe, let's say, I don't know, like the length of the roots to the uptake efficiency, or it doesn't work like that?
Yeah, so that's something that we could look at further. I think as kind of an addendum onto that is also looking at how the roots are changing the soil architecture. And I guess that even goes into using these at old legacy sites. And using some of these and kind of looking at how the soil architecture has changed and how deep the plants are actually getting is really big at understanding how well they'll actually maintain the water level within that soil, as well as limiting the kind of the dust aeration of all that dust contaminants. That being said, I haven't done it. And it's definitely something that can be done.
Okay. Yeah. And then, so when you talk about like using, let's say, some kind of vegetation to remediate the soil, is it like a certain level of contamination? I mean, doesn't it become toxic to the plant itself?
Yeah, and so that's kind of what we're seeing at the higher end in section 35, is it's becoming very toxic.
Okay.
Yeah.
And I mean, just like following up on that thought, so it's like you have some contaminants in the soil and the plants are taking it up, and then ultimately, like how does it remediate in the long term? Like it has gone to the plant, maybe, like it has reached at the end of its life cycle, then like how does that work? I'm just trying to figure that out.
Yeah, sure. So there's a few different ways that we approach this. And there was actually another university, New Mexico State University, that was looking at the later half or second cycle of this remediation project. And that's why we kind of tried to identify can we better stabilize the region, as in just using the plants to hold the contaminants within the upper soil regions so that they don't migrate elsewhere? Or can we actually remediate, which is more of the partition of the chutes? And so if you did that, then you'd have to at least kind of get some ag going through the field and actually harvest all of those plants. And you can do, who knows, with those plants in the end, depending on how much has been fractioned to them. There was talk about trying to do oil pressing out of the sunflower seeds for biofuel. There was talk about trying to grow industrial hemp, a variety of things, wild ideas, and it's still forthcoming. That's the idea of what you do with it. Otherwise, if it was too hot, then you can at least take it all and convert it into biochar and store it in a much smaller area than you would with all of that dirt and contaminants. But it's also an open-ended question of what to do with it in the end.
Yeah, that's good to know. Thank you.
Yeah.
And Craig, to follow up on what you were talking about, first I put in, this is actually not a joke. One of my son's favorite song is Uranium Fever. It's a 1955 song. It's pretty hilarious for Josh and Craig. The other one was, I am old enough that my parents, back in the day, shoe stores would have x-ray machines and you'd stand on them, think of where the x-rays go to see if your shoes fit. Just FYI, this is actually true. Just like what Craig was saying about the mill telling is fantastic sand. You just don't want to live next to it.
A lot of people got not insignificant doses from those shoe machines.
Well, mammals are fairly well adapted to cosmic radiation, or there'd be no mammals. But that doesn't mean, I don't think it's healthy for you. I'm just saying there are certain things that mammals have adapted to. So.
Well, if anybody goes out in that area and you have an opportunity, the last operating uranium mill in the United States is in Blanding, Utah, which is about 30 miles south of DOE's Monticello uranium mill tailings disposal facility. So if you ever are out there, they'll give you a tour. It's really pretty cool. It's brute force processing of rock to make yellow cake. It's pretty amazing. And with lots and lots and lots of waste. About 99.5% is waste.
Yeah. Well, I know that when I was at the Chinese site near Kazakhstan, they had what looked like basically sheds that you'd find by the side of the road, and the yellow cake was coming out the sides of the doors and things like that. So every country who does this kind of has issues with it.
Yeah. It's messy business.
It is a very messy business.
Are there any questions? Well, I think it's a great discussion, and today we learned a lot from you, Josh. Thank you very much for being.
Thank you. It's been a privilege.
Talk. Yeah, and
very cool presentation.
Very good.
Thank you.
Despite the orange.
I can't help that. Oregon State University.
Joking. Well, Craig and I just sat through Kathy's presentation. They had basically all the same colors in it. So that's actually where it was coming from. So
yeah.
So blame Kathy. I'll blame Kathy.
There we go.
So thank you, everyone. I wish you have a great weekend, and we'll see you in 2 weeks for another great seminar.
Thank you. And thank you, Nick, for running it.
Thank you all.
Have a great weekend,
Jody,
everyone.
thank you.